Welcome to the deep dive. We are jumping right into a highly unusual piece of source material today for you.
Yeah, it's definitely not your standard research paper.
No, not at all. I mean, if you've been following the state of biological signal processing, you know the current paradigm, right? You just throw massive data sets at a neural network and let the hidden layers sort it all out.
Right, the classic black box approach.
Exactly. But today we're looking at a GitHub repository that violently rejects that whole premise. It's built by a developer named Antilibode, and it's called As Resonator 2. And it features this remarkably quirky subtitle.
Yeah, the subtitle is just ring ring.
Ring ring, like I love that.
It's a cheeky subtitle for sure, but I mean, it perfectly encapsulates the exact physical phenomenon that this code is trying to prove. We're looking at a highly specialized tool from Perception Lab in Helsinki, and officially it's named the Epistemic Theory Extractor.
Though in the documentation, it is playfully dubbed the Meat Filter Analyzer.
Which is just a phenomenal naming convention.
It really is. So our mission for you today is to completely pull this repository apart. We are going to explore how this software uses uncompromising, like hardcore algebra, not AI, but algebra, to prove that your skull and the brainwave sensors attached to it literally act as a physical acoustic resonator when you speak.
Yeah, and the premise itself really challenges how we usually interpret biological data. Like, we're so conditioned to view EEG outputs as purely neurological data,
Right, like the electrical firing of synapses, reading thoughts, basically.
Exactly. But this tool isolates an entirely different mechanism that's just hiding inside the exact same data stream.
Okay, let's unpack this, because looking at the documentation, the meat filter analyzer isn't trying to decode thoughts at all. It's trying to extract what engineers call a linear physical transfer function.
Yes.
Like, it wants to map the electrical activity from the EEG directly to an acoustic speech file, a WAV file of the person's voice that was recorded at the exact same time. But it's specifically hunting for this thing called the microphonic effect. What is the actual physics happening here?
Well, the physics are entirely mechanical. I mean, when a person speaks, the initial acoustic energy is generated down by the vocal cords, right?
Sure.
But that vibration doesn't just travel out of your mouth. It propagates backward and upward. It travels through the jawbone, through the dense bone of the skull, through the subcutaneous tissue, and finally right to the surface of the scalp.
So wait, the head itself is physically vibrating, and the hardware that's attached to the head is just vibrating along with it.
Precisely. The spell, the flesh, the conductive gel, and the literal physical electrode cables of the EEG, they are all acting together as a passive acoustic resonator.
That is wild.
Yeah. So when those tiny cables shake within the Earth's magnetic field, or, when the conductive gel shifts on the skin, they generate these tiny microcurrents of electricity. And those mechanically induced currents are what gets captured on the EEG recording.
Which means the EEG is basically inadvertently acting like a highly distorted, terrible microphone.
Yes, exactly.
Yeah, it's picking up your voice, but the sound has been filtered through the medium of your own flesh and bone. Let me test an analogy here for you listening.
Go for it.
Is this essentially the same mechanism as the wooden body of an acoustic guitar? Like, the vibrating strings are the vocal cords, but the hollow wooden body of the guitar physically resonates, and that completely shapes the tone and the acoustic signature before it actually reaches our ears.
That analogy tracks perfectly with the physics. I mean, if you put the exact same strings on a maple guitar and a mahogany guitar, they're going to sound drastically different.
Right, because of the wood?
Because the density and the geometry of the resonator change the acoustic transfer function.
Yeah.
And it's the same with people. Your skull has a specific density. Your scalp has a specific thickness.
Right.
Even the exact routing of the electrode cables on your head creates a completely unique geometry.
Wow.
All of those biological and hardware variables act as the wood of your acoustic guitar. They're uniquely filtering the sound.
Hence the name, meat filter. So the tool's explicit goal is to mathematically map the exact acoustic properties of your specific head. It wants the physical shape of your biological resonator.
Right. It wants to extract the literal laws of physics governing that specific setup. But to do that, the developer made a profoundly contrarian architectural choice. The repository's documentation is almost combative about this.
Oh yeah, it doesn't hold back.
No, it deliberately and explicitly avoids using standard deep learning models to find that mapping.
And I really want to push back on this design choice for a second. Why abandon deep learning here? I mean, we rely on neural network pattern matching Precisely because biological data is just inherently messy and chaotic.
Two.
Everyone in the signal processing space uses gradient descent algorithms to cut through the noise. If the goal is to map complex, distorted EEG data to audio, isn't the deep neural network objectively the best tool we have?
Well, it is the best tool if your goal is solely to minimize the error rate of an output, regardless of how you actually get there.
Okay.
But standard neural networks rely on gradient descent. They act as black boxes. They take the inputs, and they iteratively tweak millions of internal statistical weights until the output mathematically resembles the target. They are essentially guessing at relationships based purely on statistical correlation.
So they learn to mimic the pattern, but they don't actually learn the underlying physical laws that generated that pattern in the first place.
Exactly. And when you apply that black box approach to highly noisy, chaotic biological data, standard AI is incredibly prone to overfitting.
Oh, right, because there's so much noise.
Yeah, it will find statistical connections between, say, a random spike in brainwave activity and a syllable of speech that have absolutely no physical relationship to one another.
Just a total coincidence.
Right. The network might spit out a highly accurate audio reconstruction, but it is effectively hallucinating noise. Its internal logic is entirely divorced from the physical reality of the skull.
Which brings us to the core philosophy of this repository. What's fascinating here is the specific terminology the developer uses to counter the black box. They call their alternative approach epistemic.
Yeah, and the term epistemic relates to the study of knowledge, specifically how we validate what we know. By calling it an epistemic theory extractor, the developer is planting a flag.
They're making a statement.
They are saying it's not enough to just have a computer guess a statistical approximation. We need to know how we know it.
So instead of inductive reasoning, where an AI observes like a million messy examples and generalizes a pattern, this tool relies entirely on deductive reasoning.
Exactly.
It forces the computer to use rigorous, strict algebraic methods to deduce the explicit human-readable laws of physics.
It demands a mathematical proof. It wants to generate an equation that undeniably proves, based on the laws of linear algebra, exactly how that specific biological object vibrated.
Here's where it gets really interesting, because that is an incredibly high bar. You are going from a chaotic, noisy EDF file full of raw brain activity directly to a definitive law of physics, and you have no hidden layers to hide behind.
Nope. Nowhere to hide.
To achieve that, the tool relies on an intense four-step mathematical pipeline. And we really need to look at how these mechanisms actually work for you guys. Let's start with step one, acoustic isolation.
So this is a brutal, aggressive filtering stage. The software applies a strict bandpass filter to both the EEG and the audio signals, isolating everything strictly to the mechanical resonance band of 50 to 300 hertz.
Well, wait, standard brain waves? The signals that cognitive researchers actually care about, like delta and alpha waves, those operate well below 50 hertz, right? Delta is usually like under 4 hertz.
Yeah, exactly.
So this bandpass filter is intentionally stripping out almost all of the actual cognitive neurological data.
It has to. The source notes explicitly that if you left those massive slow brainwaves in the dataset, they would, quote, blind a linear solver.
Because they're just too big.
Right. You have to remember the scale we're dealing with here. Alpha and delta waves are massive electrical voltage changes propagating across the whole brain. The microphonic effect, those tiny electrical blips caused by the electrode cables physically shaking from your voice, is completely minuscule in comparison.
Okay, so it's like trying to study the acoustic ripples of a pebble dropped in the ocean,
Yeah.
while a 50-foot tsunami is crashing over it at the exact same time.
Yeah.
If you want to see the pebble, you have to completely mathematically erase the tsunami.
That's a great way to visualize it. You strip away the cognition, leaving only the raw mechanical vibration data in that 50 to 300 hertz band. But the problem is that raw data is just a 1D timeline of voltage changes.
Right.
To understand a multidimensional physical resonator like a human head, we need step 2, topological unfolding.
Which sounds like sci-fi. The documentation mentions this relies on Taken's theorem, which I know comes out of chaos theory. But how does the software take a flat 1D line of voltage and magically unfold it into a high-dimensional structure?
Well, it doesn't use magic, it uses time delays. The physical system that created the signal, your vocal cords, the skull bone, the tissue, the cables, all of that is a complex, high-dimensional dynamical system.
Right. It exists in real physical space over time.
Exactly. And Taken's theorem states that the hidden geometry of a complex system is preserved within any single variable of that system, provided you look at its history.
Okay, let me try to ground that concept for you listening. Let's say you have an incredibly complex 3D object spinning in the air, and it's casting a flat 2D shadow onto a wall.
Okay.
If you only have the shadow, you obviously don't know the full shape of the object. But if you track how that flat shadow changes over time as the object spins, you can use those historical frames to mathematically reconstruct the actual 3D geometry casting it. Is that essentially what we're doing here?
Yes, that's spot on. The 1D EEG signal is the shadow. To unfold it, the software dynamically embeds this signal into a structure called a Hankel matrix directly in the computer's RAM.
A Hankel matrix.
Right. And Hankel matrix is constructed by taking the 1D data and stacking delayed copies of it into columns. So column 1 is the data from time 0. Column 2 is the exact same data, but shifted by 1 millisecond. Column 3 is shifted by 2 milliseconds.
Oh, I see. So you are basically giving the math a short-term memory. You are creating a multidimensional mathematical shape that represents the physical inertia of the flesh over a specific window of time.
Exactly. You've now captured the physical state of the resonator in an active matrix. Which brings us to step 3, the algebraic solver.
Okay, step 3.
We have this unfolded Hankel matrix of the EEG, and we need to map it to the target audio file. But remember, we aren't using AI. We aren't guessing the mapping using gradient descent.
Right. The tool uses more Penrose pseudo-inverses. Specifically, it mentions robust LAPACK Gelsey drivers.
Yes.
For those of you who don't spend your weekends running linear least squares problems,
Yes.
what is a pseudo-inverse actually doing here? Why not just use a regular matrix inverse to solve the equation?
Well, you can only use a standard matrix inverse if your data is perfectly square, meaning you have the exact same number of equations as you have unknown variables.
Which we don't.
Not at all. We are mapping a massive unfolded matrix of biological data to a single audio vector. The system is heavily overdetermined. We have way more data points than we actually need.
So a standard inverse just breaks down.
It entirely fails. The Moore-Penrose pseudo-inverse is a deterministic mathematical calculation that finds the best possible fit for an overdetermined system. And by relying on those LAPACK Gelsey routines, the software calculates the exact flat geometrical plane that maps the unfolded EEG shape to the target voice recording.
No guessing involved.
None. It doesn't guess. It doesn't wander down a gradient hill looking for a minimum error. It calculates the absolute geometric truth of the relationship instantly using singular value decomposition or orthogonal factorization.
But, I mean, even an optimal algebraic plane derived from noisy biological data is going to have some incredibly weak, chaotic connections mixed in, right? The math might solve perfectly, but it might still include tiny parameters that don't represent a real physical law.
That's true.
How does the pipeline handle that without falling back into the trap of overfitting?
It handles it with step 4, Occam's razor via SINDY.
Cindy.
Yeah, SINDY stands for Sparse Identification of Nonlinear Dynamics. It is an algorithm designed specifically to enforce simplicity.
And I love the language the developer uses to describe this part of the process. The source material says Cindy uses sequential thresholded least squares to, quote, violently crush statistically weak dimensional connections down to exactly 0.00000.
Yeah, the violence of the mechanism is what makes it so effective. I mean, in a standard neural network, if the algorithm decides a specific parameter isn't very important, it might apply L1 regularization and assign it a tiny weight, like 0.0000.
So the connection stays alive in the background.
Exactly, keeping the network dense and messy. SINDY operates on an entirely different philosophy.
It's iterative, right? Like, it looks at the equation, evaluates the connections, and if a parameter falls below a strict sparsity threshold, Cindy doesn't just minimize it, it completely annihilates the variable from the matrix.
It severs the connection completely, forcing it to absolute zero. Then it reruns the entire regression on the surviving variables to see if the physical law still holds up.
Wow.
And it repeats this violent crushing process until only the sparse, undeniably strong mathematical relationships remain. What you are left with is a highly refined, finite impulse response filter, an FIR filter that represents the exact unbloated acoustic signature of that specific person's head.
Which is an incredible technical achievement. But reading through the readme, what strikes me is that this four-step pipeline, this massive unfolding of dimensions and violent crushing of matrices, is completely abstracted away from the person actually using the tool.
Yeah, the user experience is surprisingly sleek.
It really is. It doesn't require a command line interface and a supercomputer.
No, the tool is built with a professional, dual-pane graphical user interface. You don't have to write Python scripts to use it. You just load in your standard data file.
Right. It natively supports EDF files,
Okay.
which is the standard format for clinical EEG recordings. Under the hood, it uses the non-library, which is this massive open-source Python package specifically designed for exploring physiological data.
Yeah.
So you literally just load your EDF in one pane and your target WAV audio file in the other.
And importantly, the Mon backend automatically resamples the audio clock to perfectly match the EEG clock, because if those two data streams are misaligned by even a fraction of a millisecond, the algebra will completely fail to find the physical mapping.
The synchronization is just handled automatically.
Exactly.
Once everything is loaded and synced, the first thing a user will notice is the sheer speed. Because the software is solving deterministic linear algebra instead of training a neural network, the physical law is discovered in seconds. The documentation proudly points out no epochs, no backpropagation.
Which is so refreshing. You aren't leaving your GPU running overnight. You just tune your parameters and hit calculate.
But the tuning process is where you actually dictate how the physics are interpreted, right? The GUI provides a few critical dials. First, you have to select the target EEG channel.
Right, so you can type in a specific electrode like EVG 132 or the cheese electrode at the top of the scalp. But if you leave the field blank, the software auto-selects the channel with the highest variance.
Oh, so it essentially scans the data to find the literal physical cable that was shaking the most during the recording.
Yes. Then you set the taken's dimensions. This parameter dictates the size of the FIR filter. For example, setting it to 128 taps. When you set this dial, you are directly dictating the size of that Hankel matrix we talked about earlier.
Right, the short-term memory.
Exactly. At a standard sample rate, 128 taps might equal a few hundred milliseconds. You are defining the exact length of the temporal memory the math uses to capture the biological inertia.
Finally, there is the sparsity penalty. This is the dial that controls Cindy. You are deciding how aggressive the violent crushing should actually be.
Yeah.
The documentation suggests starting at 0.005. At that level, the threshold is pretty low, so the math tries to capture the full, continuous wave of the biological resonance. But if you crank the penalty higher, Cindy will start aggressively severing weaker acoustic echoes, forcing the model to drop everything but the most dominant physical path.
It allows the user to decide exactly how strictly they want to apply Occam's razor to the data.
Okay, so once your dials are set, you click Extract Physical Law, and you don't get a heat map or a statistical probability curve. The software instantly prints an explicit algebraic equation to the console.
A literal mathematical proof.
Yeah. The documentation provides a sample output, it looks like. Target equal 11.000 EG 2.5 meters, 29.09 EG 3.3 meters.
And if we connect this to the bigger picture, interpreting that output equation is where the epistemic philosophy really pays off. The documentation highlights a fascinating scenario, like what happens if Cindy doesn't crush the terms?
Oh, interesting.
What if you run the extractor and the console prints out a massive long equation with dozens of consecutive time delay variables that haven't been zeroed out?
Well, I mean, my first instinct would be that the sparsity failed, like the threshold was too low and it let a bunch of noise slip through.
And that's the exact assumption you'd make in a machine learning context. But in an epistemic framework, it means something entirely different. The source material argues that an unbroken chain of coefficients is not a failure. It is mathematical proof that the skull's resonance is a continuous, unbroken transfer of energy.
Oh, wow.
Yeah, it physically proves that the flesh and bone are transmitting the acoustic wave continuously without any mechanical gaps or dead zones. The math is explicitly describing the physical wave as it moves.
That is incredible. And if you look closely at that output wave, there is a latency peak, right? Like the specific variable where the mathematical coefficient is the highest. That variable represents a precise millisecond marker. It reveals the exact mechanical delay between the moment the electrical signal is generated by the shaking cable on the scalp and the moment the acoustic recording actually hits the microphone.
The algebra is literally calculating the speed of sound traveling through that specific person's biology.
And the software doesn't just leave you staring at equations either. It leverages the sound device library, so you can instantly click a button and listen to the mathematically reconstructed audio.
Which is wild.
You can just sit at your desk and hear a reconstructed WAV file of your own voice, generated entirely from the algebraic proof of your brain sensors shaking.
It's amazing. And if you want to understand the structural acoustics visually, you can click Show Spectra. The tool takes the time domain FIR filter it just calculated, runs it through a discrete Fourier transform, and generates a frequency response bode plot.
So you get a visual frequency by frequency map of your skull's exact resonant properties. Like it shows you precisely which pitches your jawbone amplifies and which frequencies your scalp tissue absorbs.
Yeah, it's an irrefutable acoustic fingerprint, derived purely from linear algebra.
So what does this all mean? When we pull back from the LA Pac drivers and the Henkel matrices, what is the ultimate takeaway for you, the listener, looking at a tool like the epistemic theory extractor?
Whoa.
The immediate value here is just profound. It proves that our biological signals and our physical bodies interact in highly measurable, structurally sound ways. We don't always need to rely on opaque, black box neural networks to make sense of biology.
Right?
Sometimes, returning to the fundamentals of rigorous deductive math provides a much cleaner, more accurate picture of the raw physics driving our own meat filters.
And this raises an important question regarding how we build tools going forward. We are living in an era where it is incredibly tempting to just outsource our analysis to an algorithm and, trust the oracle.
Absolutely. It's the easy way out.
But the As Resonator 2 project proved that we don't have to settle for a computer's best guess. We have a mathematical capability to demand explicit, human-readable laws of physics from our data.
We don't have to tolerate the hallucination if we're willing to do the math. Which leaves us with a final provocative thought for you to consider.
Oh, I'm ready.
This highly specialized tool proved capable of mapping the continuous physical energy transfer of our skulls, proving they act as passive acoustic resonators for speech. If epistemic algebra can extract that hidden mechanical reality from a standard EEG file, what else could it uncover?
That is a great question.
Whether we are talking about other biological organs or massive man-made infrastructures like bridges and skyscrapers, what other systems out there do we currently assume are entirely silent or perfectly isolated from one another that are actually ringing out with a hidden, continuous transfer of energy, just waiting for the right algebra to unfold the shadow?
It really fundamentally changes how you view the physical world. I mean, everything is a potential resonator.
It really does. Thank you for joining us on this deep dive. Keep questioning the black boxes, and we will see you next time.